Welcome to a special recording of The World, the Universe and Us, recorded live at Neuroscience Live here at the Excel Centre in London.
It's so good to be here. Thank you for coming. Let's get straight into it, shall we? I'm Dr. Penny Sachet.
I'm Dr. Rowan Hooper.
We've got earth scientist and author Anjana Khatwa. We've got physicist Chamkaur Ghag from the UCL and Daniel Yon. He's a neuroscientist from Birkbeck. While we've got these experts on stage with us, we thought we'd just take advantage of your time and ask you to tell us something we don't know or something really interesting from your fields of research. Anjana, shall we start with you?
Oh, thanks very much. I'm a geologist, so I deal with very deep time stories about the creation and the origins of our Earth. And today I'm here at Geoscience because I've been introducing my brand new book. Here it is, if you haven't seen it already. It's called The Whispers of Rock, Stories from the Earth. And this book brings together Western scientific knowledge about the evolution of our Earth, together with indigenous knowledge and stories, and my own experiences working as a geologist for over 25 years. Now, one of the wonderful stories I shared on stage today was about the origins of the formation of the Hawaiian Islands, and they are located on a magma hotspot, a mantle plume. And essentially what this means is that there's a kind of a cord of magma that stretches from the outer core, and it moves all the way. It pumps superheated molten fluid, semi-molten fluid, up to the Earth's crust, the lithosphere, where it begins to melt the crust. So this is on the Pacific plate. And that Pacific plate is gradually migrating over that point of connection. So what happens is that the magma reaches across all rocks, it melts them, and it shoots through and creates volcanoes at the bottom of the ocean. Over time, that lava builds up into an island which will breach the sea level and form a volcanic island. And that's how Hawaii formed. The Pacific plate is moving over that mantle plume, that hot spot, and as it migrates, the volcanicity that creates that island switches off, and then it will start again and create a new island as that plate is moving over the hot spot. Now, the native indigenous Hawaiians, they arrived in the islands about 1,500 years ago, and as they traveled along this archipelago, they could see and sense that the volcanism on each island was changing. Some were weathered, some were older, and as they traveled along the chain, volcanism became more active. And they created and told beautiful stories that manifested their experience of the geological world. And the story that I shared on stage earlier was about the story of Pele, who in the legend, she is fleeing the clutches of her sister, who's very angry with her because Pele's fallen in love with her husband. And her sister, Namo Kahai, chases her, and Pele tries to escape, and she hides using her digging tool, Pa'au. And every time she digs an island to hide, she creates a volcano, naturally, because she's a goddess of fire. And her sister is drawn to those volcanic eruptions to try to murder her, which is rather scary, obviously. And so she keeps fleeing, and as she escapes, each time she tries to hide, she creates an island, which are the Hawaiian Islands. Eventually, they have a battle on the big island of Hawaii, where Pele is killed by her sister. And then as her sister is walking away, Pele rises, her spirit is shimmering, and she creates Kilauea, which becomes her ancestral home. And, every time Kilauea at the moment is very active, native indigenous Hawaiians see that as an expression of Mother Earth, as an expression of Pele, showing the islanders that she is there with them, that she's present. And I think the story is essentially an oral history of how to tell other islanders how to make their way across the sea to locate the descendants, but also it's this beautiful story of how indigenous knowledge ties in with science and helps us to feel a sense of connection with rock and landscape. I think it's beautiful.
It makes me wonder if how indigenous stories are adapting to modern times, especially with sea level rise. Do you see evidence of that? Sort of the stories being changed and interwoven with new things that are happening?
I think that's an interesting point. I think the stories evolve and change as they are told through the descendants, but how they are changing is they're advising scientists, particularly those working in natural hazards, how to live alongside natural processes. So in Aotearoa, New Zealand, Maori are working with geologists and geoscientists in kind of protecting communities from lahars. These are volcanic eruptions of ash and lava, and they are basically advising scientists in how to work empathetically, ethically with natural processes. So actually, it's the other way around. Indigenous knowledge is guiding Western science, if you like, which again is quite extraordinary when we think about it.
The other thing it just made me think of then was some geoengineering projects that they're starting to think about in Greenland, and they're actually not doing it because the local people they spoke to, after being really informed of what they were planning, this was like a curtain they were going to build to try to block off some of the water going under the glacier. They didn't want that to happen. And so at least they are engaging with local indigenous people and hearing what they want rather than just going in there and doing what the scientists want, and as might have happened in the past. Chamkaur, you're a physicist. Do you want to give us a bit of a spiel about your stuff?
Yeah, it's hard to follow when there's like gods and stuff going on with Marvel movie. In the dark matter game, we're trying to find rare interactions, rare particles, lots of particles out there, but the likelihood of them interacting with a detector, a target that we've built, is so low, so infinitesimally small, that you need very large detectors. You need to have lots of protection for these experiments. And so the very first thing that we have to do is be deep underground. So the rock comes in again here, deep geological time has allowed us to be able to get into the earth. And so, the current experiment LZ is a mile under the Black Hills of South Dakota. And it's a former gold mine, and it's sort of an absurd amount of work to be done to just get to your lab. You've got to kit up and everything and get down and everything to then go start your science. But it's one example of what we have to do in terms of backgrounds. And so I guess it's nice to, or for me, always nice to kind of think about and talk about that these experiments, when we're looking for science, we're looking for a new signal, dark matter, let's say. It's not that we'll have found dark matter. It's more that we'll have characterized our backgrounds so well that we've seen a bump on top of it. So we understand what could happen in that experiment. So when we go deep underground and we've got the rock shielding us from cosmic rays, we understand what that means. After that, we then have to construct the experiment from really pure materials, incredibly low uranium and thorium and lots of like rare earth metals that we have in rock. So we've got to make sure that all of that is incredibly, incredibly low. And then there's a whole bunch of other techniques, lots and lots of time, lots of, from multiple detectors around our central detector to analysis teams that are trying to pick out particular events. But what this is all leading to is that we came across what I think is the most fun background so far in the field. And no experiment had ever come across this. I remember what we're trying to do is sort of understand everything that is happening and then look for something on top of it. So we had understood, we've constructed this experiment very cleanly. There's only about 4 events or so at best a day happening in this experiment. And it looked like we understood where our calibrations, everything all made sense. But then it looked like somewhere around some events were misbehaving. They're just acting a little bit weird, and they're making it look like this could be signal. So, okay, there's something that no one's really seen before. Either it's a new standard model process, or it's dark matter. And what it turned out to be was that in the detector we have natural isotopic xenon, which has lots of different isotopes in it. Mostly it's xenon 131 and 129, but one of them is xenon 124. And there's only a few % of this stuff in the overall mix. And it itself will decay. It'll have a half-life, just like radiation. This thing will decay and spit out gamma rays or whatever. It has a half-life of its own, but it's a very, very long half-life. It's 1 trillion times the age of the universe. So if you had a single xenon 124 atom, you're waiting a very long time for it to decay.
Is that even radioactive? How can you call it radioactive if it's that long? Takes that long to?
It's still a problem, but the joke of it is it's still a problem for us, because when it does decay, there's still more of that than the dark matter we're looking for.
Oh my God!
Right? And so And so we eventually we figured it out. It's like, there's something funky going on with inner shell electrons when they're being liberated from xenon 124, really getting into the atomic physics of it. And on the one hand, kind of fun that we had no idea this was happening. And that's sort of the way. The deeper we get, the more sophisticated these experiments are getting. The more we're peeling back backgrounds till eventually we find one that we'd never thought of, because this is really weird. And we're always going to get caught up and think, oh, is that dark matter? Oh, no, it's another background. But the having the ability to peel back to that level now is just getting really funny for me. It's, you know,
So just to go back a bit, is this detector that's in the gold mine, is this like one of these massive tanks of ultra pure water under there, or is there a different kind of detector you've built?
It's a different kind of detector. We're very good, or we've been successful as physicists and engineers at building large detectors, like large water tanks, that have high thresholds. They're good at seeing high energy signals, so maybe neutrino beams or things like that. But they give you a big wallop of energy that you can spot. What we need for dark matter is that they need to be large, because we have to have a lot of target material in there, but they also have to be very low threshold. We need to be able to see, as I said in my talk, the equivalent of a single nucleus of a single atom moving by a thousandth of a hair's width. And so that gives you a photon or two to play with.
Yeah.
And so it's not these large ones. The current one is about a meter tall, a meter wide in a cylinder. The next one, XLZD, which is what the stand is all about, at Bulby Mine in the UK, would be something like 3 meters wide, 3 meters tall, holding about 80 tons of liquid xenon. So they're not crazy scale. They're kind of the size of that moon at the moment, and will get a bit larger.
And as you're sort of gradually peeling your way down through all the possible background, you know, casually just measuring xenon, randomly radioactively decay, is that of any use to you? Can you spin off anything out, or is that just kind of something cool you observe and you just keep going deeper and deeper?
Oh, no, it often... We absolutely spent. So, you know, the excitement is then we've just measured so in this scenario, this example, we rely on electrons being liberated and then recombining in a certain way. But it turns out that electrons coming from deeper shells are having interactions and recombining ultimately in a different way. So it has an immediate impact on all of our science, our future projections. So in terms of building the next experiment, now we have to factor in xenon 124. And so, hang on, there's actually going to be these events as well. And so measuring the charge yield or the yields of these kinds of events has never been done, and it allows us to push the lower and lower threshold as well. So it's immediately like we get very excited when it's like, oh, what the hell? Because it's either signal or something brand new that no humans ever kind of come across. And we need to understand it anyway. So often those papers are more interesting than we look for dark matter, we didn't find it. The why we didn't find it and how we're confident we didn't find it is stuff like this, the xenon 124.
It's an incredible story, and what struck me is the location of where your experiments are taking place. And I talk about the Black Hills in my book, because the Black Hills, essentially, if you don't know the geology of it, it's a granitic peak. It's a peak of granite, so magma that intruded into the crust and then cooled to form a great big body of granite. Now, the indigenous people, because the gold mine you referred to was illegally prospected, the Black Hills are the ancestral lands of Lakota First Nations, which I'm sure you have worked with when you've gone over there. But what I find extraordinary is the Black Hills are also known as Pahasapa in their native languages. You know, the heart of everything that is. And what gives me goosebumps is your conversation about kind of finding these particles, this dark matter, in alliance with this, what the Lakota know as the center of their universe. Is absolutely mind-blowing, absolutely incredible.
Yeah, no, I agree. You know, at some level, there was kind of trepidation. You know, it's like the history of the place, the Fort Laramie treats, you know, all that, this kind of stuff that is happening. And then it's like, well, okay, now it's a lab, and, you know, there were certain missions there in terms of no extraction, things being put back in. So a great kind of trying to honor and trying to, and in fact, in our results paper, we were trying to sort of expand. We had for the first time kind of acknowledgements through that, and we were trying to make it more substantial and really bring in the wisdom of it as well. So the heart of the planet, like the Amazon, are sort of the lungs of the planet, the Black Hills being referred to in that way, but you can feel it. It's a really holy. It's really odd, especially when you get out into the wilderness as well. Being able to kind of listen very quietly, because that's really, sometimes I think of these detectors as listening devices. It's just incredibly quiet, and rather than binoculars or a telescope, we're using this thing to try and hear the smallest interactions. And to be doing that in somewhere like South Dakota, the history is icky, but the actual, when dropping that and really just being with the rock, it's crazy. Like actually being inside the mine, surrounded by it. Yeah.
What's extraordinary is what you're describing is what the indigenous people, the First Nations, Dakota, they call it vision questing.
Yeah.
And they will spend days, weeks being within nature, being with the rocks, searching for meaning and story and lessons to take back. And I find it extraordinary that you as a scientist are doing that.
Yeah.
I as a geologist do that when I interact with rock. It's a beautiful synergy.
Yeah,
Thank
absolutely.
you. Thank you for sharing that.
Thank you.
Over to you, Daniel. How are you going to follow up?
Oh, it's with less poetry, I'm afraid. I've just come from the mind and body stage, where I was also talking about my new book, A Trick of the Mind: How the Brain Invents Your Reality. So I'm a psychologist and a neuroscientist, and the main arc of the book is that you should think that your brain is really like a scientist too. It's building its own theories and hypotheses to make sense of the world, but these also become the sort of lens and filter through which you see everything in the world around you and how you see the world inside your own head. But the thing I guess I wanted to highlight now was something that I think is really interesting and where the science is currently going, in that we're beginning to see how there are particular neurochemicals in the brain that seem to control how wedded we are to those theories and hypotheses, and how open-minded we might be, how easy it is for us to undergo our own kind of paradigm shift. And as we kind of begin to detect what these chemicals are, it also becomes possible you can take quite familiar drugs that already exist, drugs like propranolol, which is often prescribed for kind of anti-anxiety medication, or things like Ritalin, given its technical name methylphenidate. These two drugs seem to have effects on this system in the brain, the noradrenaline system, that tracks how much we trust our existing theories of the world and how much we're willing to shift.
And so is it a good thing to sometimes not trust how you see the world, because then that opens you up to think about other things, or is it better to trust your inner scientist?
Well, I think that there's probably no right answer in general. I think that one thing that you can see, for instance, is that though people don't necessarily combine this with drugs, this same system seems to be implicated when people undergo quite dramatic changes in what they think about the world. And those could be positive, but they also could include things like people coming to believe bizarre conspiracy theories. You can think that when this kind of chemical is surging in your head, it makes your mind more malleable, and the next message that comes in is going to have a powerful effect on what the brain thinks and feels. But you might not always be in control of the messages you're receiving. So I think it's sort of an open mind can be a dangerous thing as much as something we'd want to prize.
When you're talking about people believing conspiracy theories, are we seeing more of that? Because certainly it seems like there's much more misinformation believed around at the moment. Certainly, vaccine hesitancy in the US is a horrendous problem. There's all sorts of other issues related to that. Is there more of it around at the moment? And if so, what is, not just a small question, what's underlying it? And how do we tackle it?
No biggie. No, in short, yes. And I think that
So
maybe,
there is more of it.
and I think that people have maybe gone on a bit of a journey, right? And that I think maybe a few years ago, people would have thought that believing in a conspiracy theory was somehow to do with the individual. You would kind of explain it away as there was something particularly wrong about the kind of particular impressionability or gullibility of a particular person, and we would think, we're not like them, we think clearly. But the rates at which people are beginning to endorse some of these unusual ideas suggest that it can't just be that there are a few kind of unusual people. It seems that all of us have the potential to believe these strange things. And I think that it's probably actually connected to this same kind of system. What this system in your brain should be doing when it's working well is it should be listening out for changes in the environment. And when you start to think that things are changing, you should want to think something new. So that's kind of what this kind of noradrenaline system does for you. It means that it's easier for existing information to adjust what those kind of networks are believing when you think the world is volatile and there's change afoot. And I think maybe that's just the kind of time we're living through. There was some empirical evidence for this. For instance, during the kind of pandemic, I spoke about this in my talk, the lockdowns state by state in the US could lead to spikes in behavior that we know are connected to this system. So it looks like once you start to encounter something really unexpected in the environment, it has this effect of spiking that volatility in the brain and in turn making you open-minded, but possibly open-minded to things you might not want to think.
It's quite interesting. It makes me think a little bit of things like anxiety and depression, which we used to unfortunately see as kind of a moral or character flaw. Now we much better understand it can be to do with just brain chemistry not being quite where we want it to be. Never really thought that falling down a rabbit hole and unfortunately getting very involved in the wrong kind of ideas could similarly be something just off with your brain chemistry.
Yeah, and I think, from a sort of personal perspective, I find this science itself really fascinating. It's, it's great to sort of be in the lab doing the experiments, but on a more kind of human level, I find it quite humbling to think that when you look at how your brain is constructing that world that you live in, that grip you have on the world is always a bit tenuous. And you should maybe be a bit more humble when you see someone thinking or believing things that you don't think are right, because it's not that difficult to find yourself in that same situation.
Do you have any news you can use on how to keep your grip on reality?
Well, I'm not going to suggest that we should all just take propranolol, but that is what happens in some of the studies.
Right,
People become more stubborn in some recently acquired beliefs if they're under the influence of this drug. So maybe in the not too distant future, the way we'll get a grip on reality is by fiddling with the chemicals. I'm not saying I would recommend that, but I think we should also not be afraid of change. And this is something I actually wrote for the Neuroscientist about recently, the sense that when our brain's detecting this instability and uncertainty, it might make us feel anxious, but uncertainty isn't always a bad thing. All it really means is you don't know what's going to happen next. And having that flexibility in our minds won't just mean that we're going to believe in conspiracy theories. It will make us entertain other thoughts that we might not otherwise be in a position to. Like lots of points in human history, being in that kind of point of change can make it possible to think things that seemed unthinkable before. And lots of positive social change. Even of the kinds of changes in how we're thinking about different aspects of science we're hearing from the panel, that I think couldn't have happened without that sense of things being different to the way they were before.
Really fascinating three different perspectives there. Thank you so much for sharing those. We've got a bit of time for questions. If anyone would like to put questions to the panel or to Penny or to me.
Rowan, of course, too.
You were talking about dark matter. Have you actually found any?
No. All we have is 100 years, almost, of inference. We can see lots of evidence that suggests it has to be there, or something like it. And we can see that it has to be there at every scale. So if you look at small stuff on the size of stars or things, there has to be dark matter. We look at galaxies, we look at the largest structures in the universe. Wherever we look, it seems like there has to be 5 times more dark matter than regular matter. But we've not found it. We've not caught it in a jar or even seen it ping in a detector or anything like that. There's hints of it from space. There are some satellites that say, oh, look, we're seeing this signal, and that would fit. It's consistent with dark matter interacting in this way and giving you a signal like that. But it might not be as well. And then there's this bigger question of dark matter might not be what we think it is at all.
In your talk, you said that dark matter could interact by the weak force or something like that. Could it decay into normal matter?
Yes. Most models would predict that it would decay and it would eventually come into standard model. So to keep it stable, if dark matter is something like that, something from a boson that could then go and decay, it has to still be here 14 billion years later. So it better not decay too quickly. And so that constrains the modeling, and it can tell you that, okay, well, it can't be that, and it can't be that, and it'd have to be this, because it's still here today. And one of the symmetries that's imposed is this thing called R parity. So the R parity symmetry is what ends up giving it this kind of life and non-decay mode, such that it could even still be here today.
Any other questions in the audience?
Could being neurodiverse or having specific mental illnesses affect, I guess, your brain chemistry, and then how more likely you are to believe conspiracy theories.
I wouldn't say that I would make that jump to neurodiversity we know would make you more or less likely to believe conspiracy theories. But I think what you're getting at is really important, which is that I think once you start to think of your brain in this way as it's kind of creating these interpretations of the environment, and these will be kind of fit to your own personal experiences, and each person has their own particular balance between how they take in the information and how they project onto it. I think this might give us a new language for thinking about what's happening in different kinds of neurodiversity. I spoke about it a little bit in my talk in the case of autism, but you can think more generally that you can think of different ways of kind of apprehending the world and comprehending things as being to do with differences in the way people build those models and then have different filters. It kind of means that all of us, neurodivergent or otherwise, we're all creating the particular world that we live in any given moment. We can all be in this room, but we're all experiencing a subtly different reality that's reflecting those different ways that our own personal brains inflect it. And that's going to be to do with chemistry, but it's also just going to be to do with the experiences that each of us has as we go around the world. We don't all live in the same world because we all experience different things.
Daniel Yon, Chamkaur Ghag, Anjana Khatwa, thank you so much for joining us.
Thank you.
This has been The World, the Universe and Us. If you're not a subscriber to our show, please do subscribe. Tell everyone else about it.
Thank you for coming along. We'll be back as normal on your podcast feed soon. Thanks very much.
Thanks, everyone. Bye-bye.